Here's our last video of the semester. It's hard to believe that we made it, I guess, already. It seems really fast. And I don't know how many videos we went through together, but hopefully you learned something this semester, and this will help you out not only this semester, but maybe in the future as you go through other classes, and you can always refer back to these videos. So it's really great to have the opportunity to do this. And let's finish off in this short video by talking about polarity of molecules. So remember, if you go back to chapter 12 videos when we were talking about polar bonds, okay, that's that unequal sharing between atoms in a bond. So in this case, the electron density, it's kind of hard to see here maybe. Maybe it's just my angle of the screen. But the electron density is kind of favoring towards the fluorine atom here, away from the hydrogen, okay? And the electron density in the bond shifts to the more electronegative atom. So how do we determine then if a molecule is polar? Well, first, let's talk about what a non-polar molecule is before we talk about if the molecule is polar. So a non-polar molecule is a molecule in which there is a symmetric distribution of charge. Okay, you could say it's the charge distribution is equal in all directions. So if the bonds of a molecule are nonpolar, the molecule is nonpolar. Okay, simple as that. But there's a little more to that. If the bonds of a molecule are polar, the molecule may be polar. That's the key here. The molecule may be polar. Okay, so we have to do a little bit more investigation to figure out if it is or not. For example, if the polar bonds are symmetrical, you know, they're distributed with equal magnitude, the molecule is nonpolar. One of the ways we could think about that is, let's say we had a carbon fluorine bond here. This may be an example on the next slide, so I might be giving it away. Okay, by itself, the carbon fluorine bond is polar, which means the fluorine is taking electrons, or pulling electrons, I should say, away from the carbon. But if you look at this carbon tetrafluoride molecule, okay, each one of these fluorine atoms is taking away, or basically stealing in a way almost. It's unequal sharing, right? So they are not evenly sharing with the carbon atom in the bond, but in the molecule, all of the fluorine atoms are doing that, is what I'm trying to say. So it's like it's a tug of war, and they're all pulling with equal strength on the electrons in the carbon atom. So it's symmetrical. The carbon atom, you can think about it, the electrons in the carbon atom aren't going to go anywhere. That's not technically true, but I just want to kind of give you that idea of a four-way tug of war where everything is stagnant and symmetrical, okay? So this molecule is nonpolar. Okay, so it's kind of the idea I want to give you. It's maybe not technically right, but just kind of give you that idea of a four-way tug of war here. So if the polar bonds are symmetrically distributed and of unequal magnitude, okay, so now let's say here, okay, I did this, okay, put a chlorine there. Well, now that guy's strength is less than the fluorine, okay? Give it a little arrow. So now this is going to become a polar molecule, okay? So I actually want to write both of those down just so you have them for reference. So just for completeness here. Okay, because there's equal pooling here, and it's unequal for the other molecule. And of course, if the polar bonds are asymmetrically distributed, if we had a bent shape or a different shape like we saw before, an angular shape, that would be a polar molecule as well. Okay, so that's just kind of the idea here. Think in your mind, tug of war. Okay, if you could think tug of war with all these atoms, and will there be a net win in the tug of war in one direction. That will really help you, I think. Okay, here's some examples of polar molecules. So again, here's a polar molecule, HCl. Here's one, CO2. There's no net dipole moment. The dipole moment is kind of the winning of one side of the tug of war, if you think about it that way, in terms of where the electron density is moving. So these guys are pulling with equal force here, so there's no dipole moment. Over here, you have oxygen and hydrogens here and water, okay? The oxygen is going to pull in this direction, the electrons, right? And so the net dipole moment, if you actually look at it for this molecule, there's a net winning of the tug of war, in other words, in that direction. Things are going towards oxygen, another way to say that, okay? Here's some more examples of basically what I just did with the carbon tetrafluoride molecule. So maybe I should have just saved that for this slide to explain it. But basically, again, if they're all symmetrical around here, no net dipole moment, you change one of these atoms to a hydrogen, and now there's an asymmetric molecule. And then the polar bonds here are going to cause a net dipole moment. Excuse me. And the same idea. You switch out more molecules until now you switch them all to hydrogen. And now, again, this is a nonpolar molecule. Okay, just to kind of give you that idea. So let's just do our final example, I think, for the semester. In this, it's a momentous occasion, our final example for these videos. And you made it. Congratulations. I had faith in you the whole time. Maybe I didn't have faith in myself, but we both made it. And definitely a cool feeling, I guess, to be towards the end. So here we go. BF3, is it polar? Is NH3 polar? Okay, so here we go. We got to draw the little structures first. Do that. This is what you get. Remembering that boron can have less than an octet. Okay, so it's happy that way. Okay, and that's that molecule. So this bond is polar, right? It's going towards the fluorine, but it is pulling the same in all directions here, right? So this molecule is going to be nonpolar. And here, right, this bond is polar, so it's going towards the nitrogen in this case, and you can look on the differences in electronegativities between the atoms and go back to our section on polar bonds. But the idea here is it's pulling towards the nitrogen, and you see here there's nothing to cancel it out. It's asymmetric, right? There's nobody over here, so this is going to be polar. And with that, that ends. Maybe we should linger on it a little bit more. What's going on here? Okay, so that's polar, that's nonpolar. All right. But that ends our example problems and our videos for this semester. So as always, let me know if you have any questions. Feel free to reach out to me. And it was just such a great time I had filming these videos and putting them all together this semester. And I wish you the best on final exam and your future classes after this, and hope to hear from you soon. So yeah, I don't know how to sign off now, I guess, but just again, reach out to me if you have any questions, and I'll talk to you guys soon.